This presentation about seismic tomography visualization was created by students and researchers participating in the project entitled Integrated Analysis for the Development of 3D Models of Earth Structure. This project is part of the NSF-funded Salvage Center of Excellence of the University of Texas at El Paso. This presentation will cover 3 topics: experimental dataset, reflected tomography algorithm, and 3D model visualizations. The dataset was produced with the Potrillo volcanic field experiment, which included 8 explosions or shot points and 793 geophones or receivers. The purpose of the experiment was to examine the Earth's crust across southern New Mexico and far west Texas. Here's a location map for the experiment. You will notice that the experiment included 8 shot points. However, one shot point had a very low signal-to-noise ratio and was excluded from the dataset. The seismic tomography algorithm is used to compute a 3D velocity model of a region, where velocity is a measure of how fast seismic waves go through material. The algorithm uses rays to represent the directional propagation of seismic waves, and it computes ray coverage, which indicates how many rays intersect a part of the material. The seismic tomography algorithm includes 2 top steps, the forward step and the inversion step. These steps are performed by the lines labeled A through E, which are repeated until some stopping criteria are met. The forward step computes first arrival times throughout a discrete 3D model of the surveyed region. Depending on the computations, a discrete model can be seen as a set of vertices or as a set of cells, where each cell is bound by 8 neighboring vertices. The inversion step includes the computation of ray coverage in the region, the computation of velocity perturbations, smoothing of velocity perturbations, and updating of the 3D velocity model used for the iteration. While the stopping criteria are not met, steps A through E are iterated upon or repeated. Eventually, the model will converge or some other iteration stopping criteria will be met, and a final 3D velocity model will be produced by the algorithm. Now let's see more input-output details of the algorithm. Input data includes the geometry of the region, the locations of the shot points, and the locations of the geophones or receivers. With this information, knowledge about the geology of the region, and readings of first arrivals, an initial 1D model is created. Using the 1D model, a flat layer 3D velocity model is created for the first iteration of the seismic tomography algorithm. Using the 3D velocity model, the forward step computes a first arrival model for each of the shot points. Here you see a 3D first arrival time model for one of the shot points. Also included in this visualization is a number of isosurfaces that show the position of the front of the seismic wave created by the shot point at about 1 second intervals after the explosion. As you can see, it took about 37 seconds for the front of the wave to get to the end of this model. Here's an animation of the front of the wave for shot point 1, shot point 2, shot point 3, and so on. With this model of first arrivals, the algorithm backtraces the ray paths followed by the seismic waves from shot point locations to receiver locations. Here is a close-up of a shot point that shows ray paths to a number of receivers. As the algorithm proceeds, ray coverage from all of the shot points and receivers is combined into a single coverage model. With that information, velocity perturbations are calculated to update the velocity model to reduce the time residuals, which are the differences between arrival times observed with the experiment and arrival times computed with the algorithm. Velocity perturbations are computed only for cells where coverage is greater than 0. After that, the velocity perturbations are smoothed or smeared throughout all the cells with a non-zero coverage. And they're smoothed again to cover all the vertices in the model. Velocity perturbations are then used to update the 3D velocity model for the next iteration. The initial velocity model used for the algorithm looked like this. But after several iterations and applications of velocity perturbations, the model will converge to a final 3D velocity model that looks like this, which will be output by the algorithm and can be used for analysis of the physical properties of the region, to locate the focus of an earthquake, and for other analysis. Thank you for watching this presentation about seismic tomography visualization. This material is based upon work supported in part by the National Science Foundation under grants number HRD 0734825, HRD 1242122, and MRI CNS 0923442. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation. This presentation was recorded by Dr. Rodrigo Romero.